In the previous video, we showed that a moving charge creates a magnetic field. We showed that a moving charge in a magnetic field feels a force. And we also showed that cutting magnetic field lines induces a current. But we did not quite do what we wanted to do. We didn't quite get to showing the connection between electricity, magnetism, and light. So let's do it. Light, an electromagnetic wave. The changing electric field creates a magnetic field, and the changing magnetic field creates an electric field, and they go on forever. And we can kind of show that in the laboratory by turning the lights on and showing a capacitor and an inductor. We've already talked about simple circuits with capacitors and inductors, as simple as anything like that could be. We said that the capacitor will fight against being charged up. Throw that switch and initially lots of current flows onto the capacitor, but then it fills up and eventually the current in this circuit goes to zero as the capacitor is completely full and fights against any more changes in voltage. Eventually, after a long time, the current through this circuit reaches a maximum and everyone's happy. But it was hard to get there because that inductor fights against changes in current. It's this situation again. Connect these coils together. Chaos ensues. You try to put a current, and that's good, but it creates a magnetic field, and then the created changing magnetic field induces a current that opposes the current that induced it. It fights against changes in current, this inductor. And that's a bit of a horror show, and I agree. Here's what you need to know, that an inductor fights against changes in current. So let's take that capacitor and that inductor and put them together. And we'll use this applet to figure out what happens. Again, we have a switch over here. Close that switch and charge up the capacitor. Open that switch, close the other switch, and we'll let that capacitor and that inductor talk to one another. So let's do it. Now, as I said, we'll start by closing this switch to charge up the capacitor. Got fully charged, that looks good. Open the switch on the left and then close the switch on the right. Capacitor and inductor working together. We'll let this run for 25 more seconds and make a graph of the current versus time. Once again, we started with a charged up capacitor, and now we're going to throw that switch and see what happens. We throw the switch, and that capacitor doesn't like being charged. Those positive charges don't like each other, so they want to run off that plate, and as they do, they put a current through the circuit, through the inductor, and the inductor fights against that. That current would be huge. That current would be an exponential decay. Be kind of infinite if there was no resistor, but there is an inductor that fights against changes in current. It fights against changes in current and slows you down, and then we have a maximum current, but look at that, the capacitor is totally discharged now. Current is a maximum, and we're all done, only we're not, because the current wants to stop now, but the inductor won't let it stop. The inductor fights against changes in current, so as the capacitor is totally discharged, the inductor pumps charge onto the other plate. The inductor resists changes in current and it pumps charge onto the other plate. And then we have the same situation, only opposite. You could say that the pendulum is swung to the other side here. We have a charged up capacitor and no current, and then those positive charges don't like each other, so they run off the positive plate and through the inductor, and the inductor fights against the changes in current, and then the capacitor is discharged, but the inductor has a big current through it and will resist the dying off of that current, and we go back and forth and back and forth. And you can think about this in terms of energy. You could think about this in terms of the energy stored in the capacitor and the energy stored in the inductor, the energy stored in the electric field versus the energy stored in the magnetic field. You could think of this in terms of simple harmonic motion, sines and cosines and springs and pendulums, and we're back to all that from earlier in the course. Or you could think of this as an electromagnetic wave. Now, all of those equations that we skipped over earlier, those equations involve these constants. Epsilon naught and mu naught. Epsilon naught is the permittivity of free space. Mu naught is the permeability of free space. They are kind of confusing, I guess. The details are not super important, except that if you put all the equations together, you can find the speed of light, the experimentally verified speed of light through those constants. So like I said, our job was to try to hook together, unite electricity, magnetism, and light. And we did it with these constants. And we did it when talking about refraction. Refraction, we talked about light changing direction as it entered a new medium. Why did it do that? Because it changed its speed. Well, the speed depends on epsilon and mu, how that medium responds to electric fields and magnetic fields. And we've talked about how a dielectric material responds to an external electric field. And the deeper you get into the equations, the more fundamental the connection is. And we can thank James Clerk Maxwell for working out the details that are surprising. Every bit as surprising as when Isaac Newton discovered showed the connection between the physics down here on Earth and the physics in the heavens.